So first things first, just to get some vocabulary out in the open, when we're talking about a degree, which is a unit of angular measure, you've talked about a degree before in geometry class in like forever. A degree is technically defined as a unit of angular measure equal to 180th of a straight line. So if you think about a straight line, when we took geometry, you had the straight line. How many degrees was this? 180. So when we define a degree, we're just saying that it's 1/80th of a straight line, so it would take 180 of them to make the straight line. The definition kind of defines itself, kind of weird. When I'm talking about revolutions, which we'll hear in these units, I'm talking about a full rotation around a circle. So just knowing about that word. But what we're going to deal a lot with is central angles for circles. The central angle, the variable we're going to use for it is no longer going to be x or y, it'll be a Greek letter, usually the letter theta. That's how you say that. So it's a circle with a line through it. It's called theta. That's just any angle that we're measuring from the inside of a circle. Okay, it might be theta, it might be alpha or beta, but they're going to be Greek letters from here on out. Arc length is S. Weirdly enough, S stands for arc length, even though there's not an S in arc length. When I'm talking about arc length, I'm talking about the section of the circle contained in that angle. So like the angle makes like a bloop, little alligator mouth. The arc length is the arc of the circle contained by that alligator mouth. And obviously we know radius. Radius is the distance from the center of the circle to the outside, to the circle itself. It'll be the same around the whole circle, which is very helpful to remember. Are these things we sort of remember? Okay, great. Something you probably have not used before is the degree measurement called degrees, minutes, seconds. It's very helpful in longitude and latitude. Do y'all know what that is? I know we don't do maps a lot anymore, but longitude and latitude is like how you position around a globe. It's a circle, so you need degrees. But we don't want to use like 5.8 degrees because that's not really that specific for navigation. So we created what was called degree, minute, second mode, where the first part of degrees, minute, second will be degrees. And then the first number with the tick mark, that's called minutes. And then the number with 2 tick marks is called seconds. So we would pronounce that 62 degrees, 32 minutes, 15 seconds. And it's just a more accurate reading of a degree, so we don't have to use decimals when we're doing degrees. It all has to do with like a clock, basically, 60 minutes in 0.1 degrees, and on like that. So we'll do some conversions with those in a little bit. It's not that bad. But the angular measure that we're going to do a lot in this class that's probably new for you is called a radian. A radian is a unit of angle equal to the angle at the center of a circle whose arc is also equal to the length of the radius. Feels like a lot of the same words in that definition, and you're right. It's kind of confusing until I explain it a little bit better. We're going to spend a lot of time on that today. But very quickly, if you were to look at this circle, we have our radius here, obviously, which means this is also technically a radius, right? Because it's the same going out to the circle. A radian theta, so this measurement right here would be considered a radian if this distance right here was the same length as the radius itself. So this radius is equal, let me use the arrows. This radius is equal to this radius, and the distance is equal to this distance. Yes, it's curved, so it's not making a perfect triangle. It's not an equilateral triangle because this is curved around a circle. But if you were to measure that arc length, it would be the same distance as the radius. If that's true, so equal, 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 then this angle theta is considered to be a radian. So the radian measurement will change as your circle gets bigger or smaller because it depends on what circle you're using for how far a radian is, if that makes sense. But the ratio of it, because all circles are similar, will be the same. We will be using a lot of radians to measure circles instead of degrees because it lends itself to better trig as we get further into the unit. So just know there's a difference between measuring in degrees and measuring in radians. Especially there's a difference on your calculators. There's like a whole mode setting you have to switch to go from degrees to radians. But we'll worry about that next time. We're just going to worry about converting from degrees to degrees, minutes, seconds, and degrees to radians today. That's kind of the main idea. So we're going to convert these degree measurements from degrees to degrees, minutes, seconds. So like I said, 37.425 degrees is a way you could measure an angle, but it's not probably the best way. If we put it in degrees minute second mode, all we're going to do is take the decimal portion of the degree measurement, so 0.425, and we're going to multiply it by the conversion factor that 1 degree is 60 minutes. Now, when you're doing conversions, and if you've done a lot of science conversions, you'll remember you want the units to cancel out. So if we want to get it to be minutes, we want these degree units to be able to cancel out. So they're on opposite sides. That's how I remember how to do the conversion. And then that's just a calculator question. 0.425 times 60 minutes is 25.5 minutes. Ask your calculator if you don't believe me. But we still have a decimal, which means I want to take this decimal portion of the minutes and change it into seconds. So I will take that number, 0.5, and I will multiply it by the conversion. So it's 0.5 minutes, which means minutes needs to be on the bottom. Minutes is the 1 tick mark. And seconds will need to be on the top. But there are 60 seconds in every minute. So 60 seconds is 1 minute. The minutes will cancel each other out. And then we just have 0.5 times 60 seconds, which is 30 seconds. So you would write this number, the full thing, as 37 degrees, because that was the beginning, 25 minutes, and 30 seconds. That's the very accurate version of that decimal degree. It's just another way to measure degrees that, especially when it comes to navigation, is way easier to use. Questions, because y'all are going to try to be on your own. No? Okay, try letter B on your own, please. When we did that first conversion, did I have any decimals left? No, so I don't even have to go to seconds because there won't be any seconds because there's no more decimals. So this 21.2 degrees in degrees, minutes, seconds would be 21 degrees and 12 seconds. Sorry, minutes. 21 degrees, 12 minutes. If there had been another decimal at the end of the 12 when we did that conversion, that's the number you would use to go to minutes. And it shouldn't continue having decimals after that for the most part. We can also go the other way, which I think is easier as long as we remember the conversion factors. So if we have degrees, minutes, seconds, and we want to go to degrees, you can do it in one fell swoop on your calculator. We know that the degree part will be there. Great. But then we need the minutes and the seconds to convert back to degrees, which means for the minutes part of this, you will take the minutes and convert it to degrees. So you divide by 60. Since we multiplied by 60 to make it into minutes, you would divide by 60. And then to take the seconds, we're not going to divide by 60 because that would be converting it to from minutes to degrees. We're going to have to double that. And by double that, I mean not 120, I mean square it, double it. So we actually will divide by 3,600 here. Since there's 3,600 seconds in 1 degree, it's 60 times 60. Since we had to do that conversion twice to get to seconds, we technically do it twice to get back to degrees, which would be 60 times 60. Well, that's something I can throw in a calculator all at once. And if you do that, you'd get 13.4608 degrees. Once you convince yourself that that's correct, go ahead and try question B. That one's for y'all. When you do part B, we should have gotten 42.41 degrees. Is that what y'all got? Fabulous. Okay, so really converting back and forth between these types of measurements is like converting between feet to inches or yards to meters. Like there is a conversion factor between these. They're measuring the same thing in different units. That's basically all this is. Now, we're going to skip actually, not to the page that's on the back, but we're going to do some of the problems over here. Because we just converted from degrees to degrees, minutes, seconds, we can also convert from degrees to radians. And all it takes is a conversion factor. We'll go back to that page in a second. Degrees versus radians. This one, very important, and we will be doing a lot of converting from degrees to radians throughout this class. It should become like second nature almost to do it in your head, because they're generally pretty easy to do in your head. If you are wanting to go from a radian to a degree, this is the conversion factor you would use, 180 over pi. If you were trying to go from a degree to a radian, the conversion factor you use is pi over 180. So literally, they're just flip-flops of each other. That's all we'll multiply the number by, and then voila, we've already got our radian or degree measurement. Now, we are not going to press the pi button on our calculators to do this, and we're not going to use 3.14. We're going to leave pi in the answer. So when we're doing 90 degrees and converting it to radians, I would be doing 90 degrees times pi over 180. That's the conversion factor to go from degrees to radians. Here's how it's easy to do this in your head. When you are multiplying a number by a fraction, if there are similar numbers on the top and bottom, you can basically factor them out. Meaning, I can say, all right, look, there's a 0 here and a 0 here. I can just get rid of them. They cancel each other out. It's like dividing by 10 on both sides. Those numbers are both divisible by 10. But then again, you notice 9 and 18. What's 9 divided by 18?
2. Wait.
That's 18 divided by 9.
Oh, my bad.
Flip that number over. Not 2. 1/2, which means we have 1/2 times pi, or pi divided by 2. Because this is 1/2 times pi. We just don't put the 1 there. And I'm done. Obviously, you can use a calculator if you need it, but this is the sort of stuff that you want to do quickly because it's like the breath before you even do the problem. So this shouldn't be something we take time on. But I know we're learning, so we'll try it again. Okay, we convert from 150 degrees to radians. 150 degrees times pi over 180. Again, to be able to do this quickly and save some time, I see that they both have zeros, so I'm going to cancel out the zeros. And I have 15 and 18. What are both 15 and 18 divisible by? 3. What's 15 divided by 3? What's 18 divided by 3? So this answer is 5 pi over 6. Using that same idea, can y'all do letter C? Try to do it without a calculator. Obviously, it's there if you need it, but try it without it. Okay, here's how my brain processes this. Negative 210 times pi over 180. Well, 210 and 180 can cancel out the pi's. Then I have negative 21 and 18. Those numbers are both divisible by 3. So if I take that out, this would be 7, this would be 6. So this is negative 7 pi over 6. And again, we can go the opposite direction. So if I give you a radian measure, you can put it back in degrees just by flipping over that conversion factor. The way I remember it, and try to make sure I'm not using the wrong conversion, in radians, you want a pi there. In degrees, you do not want a pi there. So this pi over 10, if I want it to change it to degrees, I know the pi's have to cancel out, so put the pi on the bottom so it cancels out. That means 180 goes on the top. It's just a quick way to remember which one to use. But again, the doing it in your head bit kind of makes sense here. What will for sure cancel out? The pi's. What else will for sure cancel out? The zeros, which means this is how many degrees? 18 degrees. Let's do 5 pi over 3 together. And yes, we're going to try it without a calculator because we can do it in our brain. If we're taking 5 pi over 3 and we want it to be in degrees, again, the pi's, why did I put an equal sign? The pi's need to cancel, so the pi will go on the bottom. That means 180 is on the top. What for sure cancels? Good. Ooh, I don't want to multiply 5 by 180 in my head, so what else can I cancel out? 3 and 180. What's 180 divided by 3? Or what do 180 and 3 have in common?
60.
3, so if I could divide it by 3, that's 60. Well, 5 times 60, that's a lot easier to do in my head because it's really just 5 times 6 and add an extra 0. 300 degrees. Here's an important note I want to make before we get too far. I'm not sure if you notice, but every time, and I'm notoriously bad at doing this, so be better than me. Every time you write a degree measurement, what do you have to write after it? The little degree symbol. Because is there any symbol that follows a radian measure? No. So if you were to answer for me 18 as an angle measurement, that would be 18 radians, unless you put the degree sign. Yes, there's no pi in it, but like it can be 18. That's fine. It's just like a number, right? 18 pi is also just a number. It's just multiplied by 3.14. So if you're intending for it to be a degree, make sure the degree measurement is there. Otherwise, you're measuring in radians. So that's important. Okay, this last one is for you to try. It's a little bit of a challenge, but you got it. You can still do it in your head. And if you're like, it ain't going to work because it's 9 o'clock in the morning, you have a calculator. Okay, if I were doing this one, I would take 17 pi over 3 and multiply it by 180 over pi because I want the pi's to cancel. So bing, boom, they cancel. And now I have some ugly numbers. I don't want to do 17 by 180 in my head. But again, 3 and 180 will reduce to 60 over 1. And 60 times 17 is still a little bit ugly to do in your head, but you can, if maybe you have to do this whole number. Leave a space for the 0. 7 times 6 is 42. That's 10. So this is 1020 degrees. Now that's a lot of degrees. So let's think for a second what that would actually look like on a graph, just for funsies. If I do this, how many degrees have I traveled? Well, for a circle is how many degrees? 360. So that's 360 degrees. That's one revolution. If I go another revolution around the circle, how many degrees is that? 720. How many degrees are left for me to get to 1020 if I'm at 720? 300. Oop, that was ugly. Let me try again. That is what that angle would look like. It's 2 complete revolutions, and then you get to the 4th quadrant still. So that's a very dramatic angle, but that is technically an angle along a circle. You would just revolve around the circle twice before you finish at the terminal angle. We'll talk more about that next time. It's just for funsies, looking ahead. We're going to be doing some loop-de-de-loops around our circles. Now we're going to take a pause for a second because I have a feeling that you have this question in your head. Yeah, but what exactly is a radian? Why are we doing something other than using degrees? And that's a really great question. So let's just explore for a second what a radian is. Grab a highlighter out of the bin. This would be easier to probably do with highlighter. And then listen for a second while I explain what I'm trying to get you to do. With the highlighter, you're going to start at the center of your circle and draw just a radius. But think about how long it takes you to draw that radius when you do it. So for me, it's like 1, 2, 3. 3 seconds of drawing. So do yours, whatever your number is. However long it felt like you were drawing for that, I want you to now draw along the curve of your circle. So for me, it was like 3-ish seconds. 1, 2, 3-ish. Do your best. We're not measuring anything on purpose. We're just trying to get the idea across. So like technically, you've drawn the same distance for the radius that you drew on the arc, correct? Approximately, because we're just like guessing how far we've drawn. Okay, we're going to close that up with another line. This is, again, just another radius. Because anytime it goes from the center of the circle to the end, that's a radius. If you think back to geometry, there's a symbol to indicate that a length of a side is the same length. Do y'all remember that little indicator? It's like a little tick mark on it, right? So we can say, like, these two lines are the same because they're both radiuses. And we're bending the rules of geometry for a second right here, because technically, this is the same distance. No, it's not exactly the same, so that's not the good use of that symbol. But that distance right there along the curve is the same distance as the radiuses you've drawn. So it's not an equilateral triangle because it's curved, but it's essentially the same distance on the first radius, second radius, and the curve. That means for this circle that we have here on our paper, that theta is a radian, 1 radian. Okay, so let's do this again. Maybe switch colors of highlighters for you for a second. Maybe find 2 more if you have some. If you don't care about color, that's fine. We're going to continue doing that. For me, it's 3-ish seconds of drawing along a circle. So I'm going to do it again. Maybe in a highlighter though. 1, 2, 3. 1, 2, 3. And then like a little extra. About how many of those distances, of those radiuses, did it take me to get around the top of this circle? 2. I've got this distance in blue. I've got the distance in green. And I've got the distance in purple. And then like a little bit extra. So if you were to approximate how many radians are in 180 degrees, which again, we are totally approximating because we're not measuring anything right now, about how many radians are in 180 degrees? 3 and a little extra, right? It took me 3 of those like colors and a little extra, going the same distance every time, air quotes, because 100% I know it's not the same distance. We're not measuring anything. It took me about 3.1. Oh, does that number sound familiar? 3.1 is approximately close to what number? 180 degrees is exactly equal to 3.14159265535, whatever. It's pi. That's exactly why we have pi. This is how they found it. They were figuring out about how many radians it would take to get around a circle, and they got to this number every single time they drew a circle. And so we have this constant of pi to tell us how many it would take. So then my question for you is, if we wanted to go 360 degrees around this circle, what would be that radian measure? 2 pi. And then you remember when we did 90 degrees on the paper just a second ago, and we said how many radians 90 degrees is? How many did we say? If you have to flip your paper over, that's fine. Pi divided by 2. Isn't 180 divided by 2 90? That's where we're getting all these measurements from. So this 90-degree angle right here, this measurement would be pi over 2. This measurement would be pi, and making it all the way around the circle would be 2 pi. That's how many radians we'd have, and that's why a pi is included in all of the radian measures. Because to make 180 degrees, you would need 3 and a little extra radians every time, which is pi radians every time. So again, understanding what a radian is going to take some time because it's probably not something that's intuitive yet, but we will be using it so often. That's what we're measuring every time, the number of radians in the circle. But let's go back to the problems on the last page. We'll leave radians for a second and go to arc length. So arc length it's got some formulas. Remember, arc length was the distance around the circle, the thing we've been estimating this whole time. We can actually find it. Remember that S is the arc length, theta is the angle, and R is the radius of the circle. Now I have 2 formulas for arc length depending on what you're measuring in. They are technically the same formula. One of them just includes the conversion factor to degrees. So when we're doing arc length, we usually want it to be in terms of radians, but sometimes we'll need it in terms of degrees. So just depending on what you use, you will either use the radian measure, which is just R times theta, or the degree measure, which is R times pi times theta over 180. It just includes the conversion factor to get it in terms of radians, so you don't have to do that separate in the problem. Now, knowing arc length lends itself to a lot of real world or like real world. Example 6 is real world. It's kind of funny. Kinds of questions you can answer. But example 5 is actually pretty cool. The running lanes at Emory Sears track at Bluffington College are 1 meter wide. The inside radius of lane 1 is 33 meters, and the inside radius of lane 2 is 34 meters. We want to know how much longer lane 2 is than lane 1 around one turn. Okay, so think for a second that we're on a track, and we have, a track shape. Oh, look, it looks like a semicircle. You're probably going to want to draw this because we're going to use this for a bit. Make mine look better. Now it's a semicircle. In this track, we have 2 lanes. I have lane 1 and lane 2. Because around the curve of a track, it looks like a semicircle. The information I've been given is that the inside radius of lane 1, so this distance right here, inside radius, is 33 meters. It says the inside radius of lane 2 is 34. So this distance is 34 meters. Now I'm not making that an angle on purpose. It's just because I'd have to write over the same number to do that distance, so it's not on an angle on purpose. We want to know how much longer lane 2 is than lane 1 around one turn. That's this entire distance. How many degrees is this entire distance? 180. So we already know that theta is going to be 180. Let me use a different color actually. 180 degrees, and we're going to do this in terms of radians. So think back just a second, we answered this. What is 180 degrees in radians? Pi. That's a degree measure, or that's an angular measurement. It's in radians. We just want to know how much longer lane 2 is than lane 1. Okay, great. We can figure that out. Let's figure out the distance of lane 1 and the arc length or distance of lane 2 around this curve and see what their difference is. We have formulas for that. If we want to find the arc length of lane 1, we're going to take the radius of lane 1 and multiply it by theta, and vice versa for lane 2. The arc length of lane 2 is going to be the radius of lane 2 times the same theta, because we're going the same distance, 180, or pi. Which means this is just going to be 33 times pi, because the radius is 33, and the theta is pi. And this would be 34 pi. So what's the difference between them? How much longer is lane 2 than lane 1? Don't overthink it. 1 pi, right? Because we'd be 34 pi minus 33 pi means that it's pi radians longer. Remember again that pi is 3.14. If you've ever seen a track meet, when they start a track race, they always start on the curve. Well, that's not necessarily true. Long distance races, they start on the curve. Does everybody start at the same point? No, they're like staggered up. Guess how far they're staggered? 3.14 yards. This is how we decided how much more to give each person as the lanes go out to make it an equal distance as they go around, so that they're all actually running the same equal distance and nobody has a big advantage being on the inside lane. Even though there's an advantage to the inside lane. We all know this, but this is why. Trying to equalize it out. That's pretty cool, I think. And then we have a real world problem that is funny, not as interesting. So let's say you're super hungry and you're just dying to eat this pizza, and then a thought hits you, you're like, I wonder what the perimeter of this piece of pizza is. Great, we can figure it out now. Let's say you have a ruler and you have a protractor. We can now know what it is. We want to find the perimeter of a 60-degree slice of pizza where it has a 9-inch radius. Here's my poorly drawn piece of pizza. This is the correct. What did I say? 7. Y'all know. Okay, here's my piece of pizza. I'm going to decorate it because I feel like it. It's pepperoni. I measured, / they also tell you when they tell you the size of the pizza, like, okay, this was a 7 inches, which means this is 7 inches. The only other thing I need to find the perimeter of this pizza is this arc length. To find arc length, I have a formula that says that the degree, using degrees, it's going to be r times pi times theta over 180. This is from the little box on your notes. And I'm using this one because they gave me a degree measurement for theta and not a radian measurement. So this theta is 60 degrees. You can't really see that. 60 degrees. So we fill in everything we know for this arc length. We know that the radius of this pizza is 7. We know that the theta we're using is 60. And we're going to divide that by 180. Now this one, since we're measuring in inches, we're not going to leave in terms of pi. But a lot of times you will leave these sorts of things in terms of pi. Inches, we don't measure like 7 pi inches. It's not a usable thing if you were really trying to figure out the perimeter of your pizza. So go ahead on this one and use the pi button to figure this out. You would type in 7 pi button times 60 all divided by 180. Please don't ever put in 3.14. We're going to be more accurate than that. We're going to use the pi button. This arc length is approximately 7.33. Agreed? Inches. Which means the perimeter of my pizza, since I'm so concerned about how long my pizza, or the perimeter of my pizza, is going to be the radius plus the arc length, which is 21.33 inches. So if you were ever eating a piece of pizza and worried about the perimeter of your piece of pizza, you now have the skills to be able to decide the perimeter of your piece of pizza, assuming that it was cut correctly and both of the sides are the same, which you could have a ruler and check. But that's fun. Look, math at the dinner table. We're going to skip example 7 because we have an activity to do. But this formula is really pretty easy to use. Just like plug in what you know and make sure you're using the correct degree measurement or radian measurement.